This is a generalization of an SMO problem where k is equal to 2025, and I thought it was an unusual, they do a lot of year problems. So 2025, of course, is the year of the competition here. And anyway, when I looked at the solution, I thought we need to generalize this. And so here's the form. This was exactly the problem if you replace k with 2025. And I guess the restriction we need to put on k in general is that k has to be greater than 0. Because it'll end up functioning as a base. Now, I guess you can have a negative base, but most of the time we're not too interested in that. A little pet peeve of mine regarding the logarithm notation. If I had my druthers, I would do this more often. To me, it's more legible just to let you know that these are functions. All right, so like right here, you would actually envelop the 2 in parentheses. Now again, that looks a little cumbersome, but if you just take a look at this, it's almost like, I guess people understand it, but if you don't write it carefully, it looks like you have exponents all over the place. So I like this notation. I will omit it just because that's the current convention that's being observed, but I think some clarity would be added to actually insert these parentheses. Now, what we're supposed to do is actually find the value of m. All right. Now, one of the motivations for talking about this change of base formula, let me just write that down. We're supposed to get this in terms of log base 2 of some value, and then that'll be our answer. All right. But we have log base 2 to the k. We have log base square root of k here. So we're kind of a long ways from that unless you are familiar with the change of base formula. Now, let me just write down a form for that that's convenient for our purposes. If you have log, and I'll just use the conventional letter b, log base b of a, and I will put the parentheses here, okay? Because it is a function, folks, no matter how you want to cut it. All right, so you can, the so-called change of base formula, you can pick any logarithm at all. So we're going to pick 2, right? Log base 2. So this is equal to a quotient. And I think if you look back at the meaning of the word logarithm from a long time ago, it actually means quotient. All right, Wei Tan talked about that at his site. But you can write this, and this is kind of spatially mnemonic. You can tell, it's easy to remember is what I'm trying to say. So you can have this as the quotient of a more relevant logarithm, and log base 2 is relevant for this particular problem. Okay, y'all, again, this is the change of base formula. And so actually we're going to use that a few times here. All right, so here's our original problem. Now I use the change of base problem right here for this part. For this circle part. Okay. You can see that the k remain unaltered right here, but I did the change of base in other words, this circle part is equal to this by our change of base formula. Okay, and in a similar fashion, I used it on this piece right here. Okay, in other words, let me just circle this piece. Okay. So you see, we did the change of base formula twice. And this circled object is the same as this object right here if you apply the change of base formula, okay? Now, why are we doing that? Well, we have to get it in terms of, we want it to be log base 2 of something, right? Because if we can get it as log base 2 of something, the something will be our answer, all right? Now, what do we do on this very next step here? Okay, we have k times log base 2. Now, oh yes, another nice rule is log base, and this is true for any base, but I'll write down log base 2. And I'll write down 2, let me put the parentheses, 2 to the n, let's say. And this is just a statement that log in the exponential are inverses, okay? You can see that's the law that I applied right here. Log base 2 of 2 to the k is just k, and you can see we're going to get this nice cancellation here. All right. Now, and again, we did the very same thing right here, and we applied this law, except it was just 2 to the 1, right? So you can see what happened here. We inverted and multiplied, and you have 2 over 1. Log base 2 of 2 to the first power is 1. The logarithm function returns an exponent. So that's why we end up with this right here, 2 times log base 2 of the square root of k. Now remember, y'all, square root of k is the same thing as k to the 1/2, right? K to the 1/2. So you can see why that 2 disappeared. You see how the 2 goes poof over here? Kind of neat. And then also the radical disappeared because the 1/2 comes around to the front. That's another property that I didn't write down, that the exponent drifts around to the front. Did not write that property down. Okay, but it's what we used to get from here to here. Now we have something in a very, very familiar form right here. The well-known, it's the most hackneyed rule in logarithms, is the log of the sum is the log of the product. All right, so we would get that this is equal to log base 2, and literally you just put them together, folks. So this, remember, the square root of k is the square root of k times the square root of k, right? So this would be the square root of k, and just hopefully in the name of readability, I'm gonna go ahead and envelop that in parentheses. Okay. But you see, remember, what were we looking for? We were looking for log base 2 of m, right? Log base 2 of m. Log base 2 of m right here. So I'll go ahead and call that log base 2 of m. Okay, and so by inspection here, the well-defined function, you get that m is equal to the square root of k quantity cubed. Okay. Now, so for the problem, that meant the answer for this particular problem in the most recent competition, problem 2, that would mean that the answer was what's the year again? 2025. I should remember. Yeah, 2025. The square root of 2025. Quantity cubed. Now, a lot of you who just don't like this kind of notation, there's almost a motion in the United States to remove this type of notation because the kids don't go to the trouble to understand it. But this is the same thing as k to the 3/2. All right, if you love that stuff so much. But this kind of hides the mystery of what the thing really is, in my opinion. But in any event, they accepted this answer. It was a multiple choice question on the SMO. All right. Okay, folks, and again, I did leave out a couple of rules. The log of the sum is the log of the product. And also, what else did I leave out? I don't know if there's anything else. Oh yeah, the exponent rule. Let me go ahead and write that down. If you have log base 2, any logarithm, right, is like this, but if you have log base 2 of, let's say, b raised to the m, bm, all right, you can let the exponent drift out to the front, and you can see why that's true if you just consider the laws of exponents where you multiply exponents under certain circumstances. All right, so this is log base 2 of b. We use that rule somewhere. Oh yeah, we use that rule right here. Or on this piece right here, folks, we used this rule because we could think of this as k to the 1/2, and that's why this 2 disappeared going from here to here. You see how from here to here, this is k to the 1/2, comes around to the front and kills the 2, and you got log base 2. Okay, we appealed to this rule right here. All right, folks, that is all. This is the final answer. Let me come up here and write it. M is equal to the square root of k quantity cubed. Generalization of an SMO problem.